Chapter 1, Exercise 7, A to G. Use proposition 118b to conclude that b to the n greater than or equal to 1 for any positive integer n. Use binomial identity to factorize b to the n minus 1 and use b to the n greater than or equal to 1 to obtain the required inequality. Generally, that is for all parts, remember that b to the n greater than 1 for all integers n greater than or equal to 1 since b greater than 1. Since b greater than 1, using proposition 118b, we have that b squared ultimately greater than 1. It follows by induction that b squared greater than or equal to 1 for any positive integer n. Furthermore, by direct calculation, we have this. Thus, we have this. Therefore, we get b to the n minus 1 greater than or equal to n b minus 1. Prove that b to the 1nth greater than 1 and use part A. Note that b greater than 1 implies b to the 1nth greater than 1. Indeed, if b to the 1nth less than 1, using proposition 118b, we would have that b to the 1nth squared ultimately less than 1. It would follow by induction that b equals b to the 1nth to the n less than 1, which is not possible. Replacing b with a equals b to 1nth, in part A we obtain this. Thus, we showed that b minus 1 greater than or equal to n b to the 1nth minus 1. Use proposition 118b to prove that n t minus 1 greater than b minus 1, and then use part B. Suppose that n greater than b minus 1 over t minus 1. Since t greater than 1, then t minus 1 greater than 0. By part B, since n greater than or equal to 1 and b greater than 1. By transitivity of greater than, definition 1.5, division by n greater than or equal to 1 greater than 0, adding 1 on both sides. Use exercise 7 part C and exercise 6 part D. Suppose that y greater than b to the w. Since b to the w greater than 0, dividing both sides of y greater than b to the w by b to the w and using proposition 118b, we have this. By the Archimedean property, we can choose n element of natural numbers such that n greater than b minus 1 over t minus 1. Then, by part C, b to the 1nth less than t. Thus, we have b to the 1nth less than y over b to the w. Multiplying both sides by b to the w greater than 0, and using proposition 118b and exercise 6 part D, it follows that this. Therefore, for sufficiently large n, b to the w plus 1nth less than y. Take multiplicative inverse and use part D. Suppose that b to the w greater than y greater than 0. Then, by proposition 118, E, we have b to the negative w less than 1 over y. By part D, for sufficiently large n, we have b to the minus w plus 1nth less than 1 over y. Using proposition 115d and proposition 118e again, we have b to the w minus 1nth equals b to the negative w plus 1nth greater than 1 over y, which equals y. Use the definition of supremum and prove the claim by contradiction using part D and part E. Answers combined with 7G. Use direct proof. Answers combined with 7F. Let x equal supremum A. By definition 1.5i, the following three possibilities exist. Case 1, b to the x greater than y. Case 2, b to the x less than y. Case 3, b to the x equals y. Since x equals supremum A, if w is an A, then w is less than or equal to x. Case 1. Suppose that b to the x less than y. Then, by part D, for sufficiently large n, b to the x plus 1nth less than y. Then, x plus 1nth element of a, and x plus 1nth greater than x. This contradicts the fact that x is the supremum of a. Case 2. On the other hand, if y less than b to the x, by part E for sufficiently large n and all w in a, we have b to the w less than y less than b to the x minus 1nth. By remark at the end of exercise 6, we have that w is less than x minus 1nth for all w in a. In other words, x minus 1nth is an upper bound of a and x minus 1nth less than x. This contradicts the fact that x is the least upper bound of a. Case 3. Finally, we conclude that it must be b to the x equals y. To prove part G, note that if x less than z, that is, z minus x greater than 0, then, by exercise 6, part D, and proposition 118, b to the z ultimately greater than b to the x. So there is a unique x satisfying b to the x equals y. With exercise 7, Rudin formally introduces the definition of what will be the logarithmic function with base b. The exponential and logarithmic functions are elementary functions which will be used in the following chapters. Exercise 7 says that the logarithmic function is the inverse function of the exponential. The red graph is g of x equals log base b of x, and the blue graph is f of x equals b to the x, and the black line is y equals x. Geometrically, log base b of x is the result of reflecting b to the x with respect to the y equals x line. Thanks for watching.